So hello and happy Math Day. This is the first of 4 video primers in which I'll cover some of the essential junior high math skills related to rational numbers. These are things that you'll need to have mastered and be very, very comfortable with moving into high school. In this first lesson, I'll look at what rational numbers are. In other words, some definitions. We'll look at some of the different forms they take, and finally, we'll be able to do some examples where we transform between decimal numbers and their fractional equivalents. This lesson is meant to be interactive, and you can find the 4 pages of worksheets that I prepared in a link down below. Download the PDF and print them off. It's probably best for you to follow along and perhaps pause while you think of some things and before we do some of the examples together. At the end, there are some practice questions for which I posted a solutions key, again in PDF and once again down below somewhere. Math should never be a passive exercise, so I do encourage you to follow along with the worksheet that I've provided. It'll make more sense that way. So where to begin? Where to begin? It probably behooves us to begin with some definitions so we know what we're talking about. Well, the term rational number is just a fancy way for saying fraction. By definition, rational numbers are any number that can be expressed as a ratio of 2 integers. So let me first draw your attention to the symbol we use for rational numbers. We use this symbolic Q, and you can see it up here as well. And that represents all of the positive and negative fractions and their decimal equivalents that you can represent. So rational numbers are fractions made up of integers of some sort. No decimals, but notice that the word ratio is actually in the word rationals, right? So we're naturally speaking about fractions or ratios between 2 numbers. So here's an important distinction. Not all rational numbers look like a fraction. In other words, decimal numbers can absolutely be rational, but on the other hand, there are some versions of decimal numbers that are irrational. If a number can be expressed as a fraction of integers, then by definition it's rational. And if a number cannot be expressed as a fraction, that is, if you can't find some way to transform a decimal into a fraction, then by definition it is irrational, the opposite of rational. So to put it another way, when we say a number is rational, we mean that it may be put into a fraction, not that it is. All right, so let's take a look at some examples. Well, the simplest example of a rational number is simply an integer. An integer, recall, is a positive or negative whole number, including 0. And so how do we turn integers into fractions? Well, you just divide it by 1. So 3 over 1 is the fraction version of the integer 3. 3 is rational. Likewise, negative 8 is simply negative 8 over 1. So just a clarification here, negative 8 over 1 can take different forms that all have the same value. So negative outside of 8 over 1 is one way to think of it, but this could also be expressed as negative 8 over 1 or conversely 8 over negative 1. They all mean the same thing. It doesn't matter where you put the minus sign. All right, how about this next integer, 0? 0. Can 0 be expressed as a fraction? Sure it can. You put any number, any integer over number 1. Anything divided by 1 is itself. And 0 divided by 1 is simply itself, 0. So there's the fractional representation. And then if we get even a big ugly number like this one here, no big deal. Draw the fraction line, put 428,971 in the numerator and put 1 in the denominator, and boom, you have made this a fractional version of the integer. Cool. So there's the first example. Any integer is rational by definition. Well, that's not the only form of a rational number. We can also take a terminating decimal. Any terminating decimal number we can also turn into a fraction. So let's take 1.4. Well, we'll do this in a couple of steps, okay? We'll start with making 1.4 a simple fraction over 1. Just like that. Any number divided by 1 is just itself. But the rule we use when we're writing fractions is to get rid of decimals. So I think you see here, to get rid of this decimal and put it over there, we're going to have to multiply it by a factor of 10. And if we multiply the top and the bottom by that same factor, then you don't change the value of the number. And that's useful because we want the equivalent fraction for the decimal. So if I multiply 1.4 by 10, I can get 14, and on the bottom, I'm going to get 10. All right? Cool. Okay, how about this next one? Well, let's start off by writing the simple fraction, 4.238 over 1. And I think maybe you'll see very quickly that we need to move the decimal place over 3 times. In other words, we need to multiply by a factor of 1,000. And when we do that, we're going to get 4,238 on the top and 1,000 on the bottom. Okay? Well, let's do this next one, a straight up decimal number. How are we going to do that? And it's negative to boot. Well, once again, start off with writing the fraction over 1. We're going to multiply it by a factor of 100, it looks like, to move the decimal over twice. And when we do that, we're going to get negative 65 over 100. All right? So there we have very simple translations between a decimal form, a terminating decimal form of a number, and its rational fractional counterpart. A couple of notes. First of all, if you don't trust the process and you want to double check, it's very easy to do. Just go, in this case, in your calculator, in the first case, go 14 divided by 10. You should be able to get 1.4. You will get 1.4. You can verify all of your translations into the fractional forms very easily just by doing the math, because 4238 over 1000 literally means 4,238 divided by 1000. Now, it's not as simple as that really, but functionally that's how it works. The next thing you need to keep in mind is that we usually like fractions in more simplified forms, or in the most simplified form. And 14 over 10 is not the most simple form. So if you wanted to take this further, and we will moving forward, you would divide top and bottom by 2, which would give us 7 over 5. Okay. So now we can see what's happening here a little bit, can't we? If we've multiplied by 10 and divided by 2, we've actually ended up multiplying by 5. And when you multiply 1.4 times 5, that effectively gets rid of the decimal as well, because 5 times 1 is 5, 5 times 0.4 is 2, there's your 7, okay? So we don't expect you to be able to do that simplification straight up. It's just easier to move the decimal over and then do the simplifying after the fact. But in short, we're usually going to want the fraction to be in the simplest form. Okay. So there's your second example of how rational numbers might appear to you as a terminating decimal. Well, there's one more. It's probably the most complicated of the bunch. It's a repeating, non-terminating decimal number. Okay? Because a repeating, non-terminating decimal can also be expressed as a fraction, and therefore they are rational. Now, what do I mean by terminating non-decimal? Well, 0.1 really means 0.11111 forever, just like that. All right. 0.14 really means 0.14 because the bar is over both numbers. The 14141414 repeats just like that. And likewise, the 0.147 becomes 0.147, 147, 147. And so these bars right here just allow us to be a bit more precise, but more importantly, more economical in how we express repeating numbers. It saves us time, and mathematicians are notoriously lazy. We're always looking for the easy way out. All right, so these are the numbers now that we want to try to convert into a fraction. What do we do? So the goal here is not to explain how the process works, because you've spent 2 or 3 years learning that in junior high. The goal right now is just to use the tricks to be very efficient in converting these decimal forms to their fractional version. And so the procedure is pretty simple. You take the number that's repeating, in this case it's 1, and you put it over 9. Now, how easy is that? Verify in your calculator, make sure it is as I say, Pro tip, it is. Now I want you to think a little bit about why this is so, just very quickly. If I go 1 over 10, you know that that's 0.1. But I don't want 0.1. I want a number a little bit bigger than 0.1. I want 0.111111. So what I need to do is take this denominator and I got to make it a little bit smaller, because everything being equal, when I divide by a slightly smaller denominator, the decimal form is going to become slightly bigger. There's an inverse relationship there. So that's why it's 9 and not 10, and that's why it works. And we are done. Now, it would be really nice if all problems were this simple. Well, all problems are almost this simple. Well, you start off the same way. You make a fraction. In the numerator, you put the value that repeats, and in the bottom, you put at least one 9, but as many 9s as numbers that repeat. There are two numbers that repeat on the top, so there's going to be two 9s. And once again, if you want to double check, just go 14 divided by 9 in your calculator, and you will see that we have the right answer. Cool. So remember, we're reviewing the algorithm right now. There is a very easy algebraic proof that shows why this works, and I've got a couple of videos linked down below. You can watch those at your leisure, and you can remind yourself of the algebraic proof of why and how this works. Right now, we're just doing the algorithm, that is, the step-by-steps to get it done. For 0.147 repeat as a fraction, well, you take the numbers on the top that repeat, 147, and as many number of 9s on the bottom that match the number of repeating numbers. So 147 divided by 99. Check it out in your calculator. You've got this. All right, let's add a little bit of complication now. Not much. The procedure is, write a fraction, put the number that repeats on the top, the 3 repeats, and as many 9s on the bottom as there are repeating numbers, 3 over 9, boom. If you put this in your calculator, you will get 0.33333. But now we're going to start doing that next little step. We're going to do the simplification if we can. And in fact, we can. If we divide the whole thing by 3, top and bottom by 3, then we are going to get 1 over 3, just like that. And that makes sense to you. You know that 1/3 is 0.333 or 0.3 repeat, or conversely, the 0.3 repeat is a third, right? You know that that number goes on and on. And because it can be expressed as a fraction, that makes the number 1/3 or 0.3 repeat rational. So in the next example now, we're going to add a couple of complications. First, we're going to add a number before the decimal, that is an integer, and then we've got the repeating value afterwards. And so to solve this one, we're going to do a little bit of trick. We're going to separate it into parts, because you know that this whole mess right there is really -1 times 1 plus 0.6. Pause the video and take a look at what that means. The -1 is really -1 times this whole mess here, okay? So it's just not -1 and then a positive 0.6, it's -1.6. In other words, -1 times 1 plus 0.6. If you see and understand that, then the rest of this becomes easy peasy, because we're going to break this down into fractions individually. So the negative, remember, is multiplied through. So we're going to pull it aside. We're going to express 1 as a fraction. How do you express 1 as a fraction? Well, 1 as a fraction is simply 1 over 1, isn't it? Any number divided by itself is itself. And 0.6 repeat as a fraction, well, you know that trick. It's 6 on the top because the 6 repeats, and as many 9s on the bottom as there are repeating numbers on the top. So 1 9. So there we go. Negative 1 over 1 plus 6 over 9. Now the problem with that, of course, is that you can't add fractions straight up like this if they have dissimilar denominators. This will be the subject of the next primer lesson, adding, subtracting rational numbers, but you probably remember enough to know that 1 over 1 is the same as 9 over 9, isn't it? All right, and now we're going to add the 6 over 9 over there, and lo and behold, once we do this transformation, we're going to get the negative, because it's passed through from here to here to here, negative and 15 ninths. There's your final answer. double check, put it in the calculator. You should always double check your math if you can, just to verify so you haven't made a silly mistake. You didn't accidentally go -9 plus 6, for example, because you put the negative sign in the wrong place. Who knows? All right. One last question. The last example of the repeating non-terminating number 2.832 as a fraction. Well, the first step will be to realize that this is really 2 plus 0.832 repeat. The first part we can make into a fraction very easily. 2 is simply 2 over 1. Cool. And then that last number, that 0.832 repeat, we know that trick. You put the repeating part in the numerator, you put as many 9s as you have repeating numbers in the denominator, and boom, you're good to go. But because we have dissimilar denominators, we're going to have to multiply this by what, 999, so that they have an even denominator. And when we do that, we're going to get, let's see, well, what's 2 times 999? Okay, remember, if you're multiplying this, or we're raising that to an equivalent fraction out of 999, then you've got to multiply the top and bottom. So we're going to get 1998 on the top over 999 on the bottom. And we already have this one as 999, a fraction of 999, 832. And when we add now 1998 plus 832, we're going to get, I think, 2,830 over 999. And there we go. We're good to go. So there's the 3 easy examples of different forms of rational numbers: integers, terminating decimals, and repeating non-terminating decimals. I want to do a couple more examples of repeating non-terminating decimals. Not because you're going to see them very much in high school math, but because I think it illustrates a couple of really good algebraic principles, and it gets you starting to think mathematically. All right? So these are all repeating non-terminating decimal numbers, which means that they are all rational. And so what we're going to do is convert them into their fractional form. Well, the first one is pretty easy here, but I'm going to show you a slightly different way. You know that 0.2 repeat is now, I mean, you know that is simply 2 over 9, okay? But let me show you a different way of thinking of how to get this, okay? Now, I promise not to show the why and the hows of this works, so I'm reneging on that promise a little bit. 0.2 repeat is the same as 0.2 over 0.9, okay? Check it out, make sure. Make sense? Put in your calculator, verify. And what we're doing to go from here to here is we're multiplying the top and bottom by a factor of 10. Top and bottom by 10. And so what we're going to do is move that decimal place over there, and this is where you're going to get the 2 over 9, okay? That's how it works. And knowing this is a little bit useful later on when we get to more difficult versions or examples, okay? All right, so let's do 0.02. 0.02. Well, let's start off with that little trick that I just did over here, okay? 0.02 repeat is the same as 0.02 over 0.9. Take a moment and look at that. Think about it. If it was 0.02 over 1, then you'd simply get 0.02 terminating right there. But we need a number a little bit bigger than 0.02 because those 2's continue forever, right? So we divide it by 0.9 instead of 10. Now, quite clearly, the factor we're going to multiply to get rid of the decimals is going to be 100. Okay, we have to move the decimal place over twice. So we're going to multiply top and bottom by a factor of 100, and we're going to get 2 on the top and 90 on the bottom. Take a moment, see what we're doing here. Look for patterns. Math is all about patterns. Math is not about adding and subtracting and multiplying and dividing. Nope, that's arithmetic. Math is about patterns and using these patterns to your benefit. Can we use this information and this information and this, to hypothesize what the answer to that is? Well, there's going to be a 2 on the top, We know there's going to be a 9 on the bottom. How many 9s? Only one 9 because there's only one number that repeats, but there's two of those there. See how there was one there and 1 0? Could that possibly be it? Well, you could go ahead and do that in your calculator and you could find out, but let's just do it the way we now know, okay? So we're going to take 0.002 over 0.9. We're going to multiply that by a factor of, looks like to be 1,000. Remember, we have to clear the decimals on both the top and the bottom. So 1,000 clears it from the top and gives us a bit of extra on the bottom. When we do that, we're going to get 2 on the top, and 900 on the bottom, which is what we have. So yes, indeed, that is my correct answer. Love it. Okay. So patterns are your friend, and patterns are going to be a recurring theme in high school. It's one of the things we've been trying to impress upon you ever since grade 7, perhaps even earlier if you had a gifted elementary teacher. All right, let's continue. We've got another pattern forming here. So you can't be expected to know what's going to happen to this straight off. So now we have 0.75555555. Fives go on forever. Well, the first thing I'm going to do is break this apart because I want you to recognize that 0.755555 is actually equal to 0.7 plus 0.05. Repeat. And the reason I want to do this is because you can turn each of those into their own fraction, change the denominator so they're equivalent, and then add them up, and you should be able to get satisfaction. So 0.7 as a fraction is simply 7 over 10 plus 0.05 repeat as a fraction. Do you remember that trick we used before? Put the number that's being repeated on the top, and on the bottom in the denominator, you want at least one 9. As many 9s as there are repeating numbers. There's only one repeating number, the 5. And then because we have one space, the 5 is translated to the right by a factor of 100, we need to put 1 0, just like that. So the next step now is to convert 7/10 into a fraction out of 90. It looks like I have to multiply by 9 to bring it up, and 9 times 7 is 63. 9 times 10 is 90. Plus, and then 5 over 90, and that's great because now we got two fractions out of 90. And now it's just a simple matter of going 63 plus 5 is what? 68 over 90. Boom, there you go. Put that in your calculator and double check for me. Make sure you get 0.755555 and so on. You do great. But remember that we always like to simplify. We like to simplify. And it looks like 2 is a common factor between 68 and 90. They're both even numbers, so they're at least divisible by 2. 6 and 8 is 14. 14 is not divisible by 3, so 68 is not divisible by 3, even though 90 is. So it looks like that's the only factor. When I do that division there, I'm going to get 34 over 45. So what I just did there with the adding the numbers up and seeing if that number is divisible by 3, those are your divisibility rules you learned in grade 7. They are going to be really handy for you moving forward. So if you could commit those to memory, that would be awesome. Let's do the next. We're going to attack this in the same manner. We've got a 0.7 part plus 0.075 part. 0.7 is simply 7 over 10, just like it was over there, same thing. Plus, now, how do we turn this into a fraction? Well, make a fraction line, put the repeating numbers in the numerator, put as many 9s in the denominator as there are repeating numbers, and then add as many zeros as you need. The number of digits in your numerator matches the number of digits in the decimal number, okay? So the next step now will be to raise 7 over 10 into its equivalent fraction out of 990. And to do that, we're going to have to multiply 7 by 99. So if we multiply 7 by 100, you're going to get 700, of course. So 700 minus 7 is 7 times 99, or 693. And then we have now a denominator of 990 plus 75 over 990, no change there. And now we're about ready to bring it home. If we add 693 plus 75, we're going to get 768 over 990. Cool. And now we should look to see if we can simplify this. Well, 7 plus 6 is 13, plus 8 is 21. 21 is divisible by 3, which means that 768 is divisible by 3, and 768 is divisible by 2. You know what that means? It means that 768 is divisible by 6. Those are your divisibility rules. 990, 18 is divided by 3. 990 is divisible by 2. So that means to simplify this, we can divide the whole mess by 6, top and bottom by 6. And when we do that, we are going to get 128 over 165. Always better to use the divisibility rules that we taught you back in grade 7. It saves you time, keeps you from having to go to your calculator all the time. All right, we have one last one, and it looks to be a little bit more complicated, but we're going to do it the exact same way. First thing we're going to do is we're going to break this number apart into two parts, 0.77 and 0.0075 repeat, okay? Now we can attack each side and make fractions out of them individually. 0.77 is the same as 77 over 100 plus, and now 0.007575. Remember how we do this, okay? We take the repeating numbers and put them into the numerator. We put as many 9s on the bottom as there are repeating numbers, and then as many zeros to make this number of digits match the number of place values to the right of the decimal place. That's the algorithm. So now it becomes clear that what we have to do is change that fraction to an equivalent fraction out of 9,900. And to do that, I'm going to have to multiply the top and bottom by 99. I think 100 times 99 will give me 9,900, like that. And 77 times 99 is going to be the same as 77 times 100, which is 7,700 minus 77, which is going to be what? 76 and 23, I think. Yeah. 76, 23 plus 77. Yep, that'll be 7,700. See, I'm doing some mental math here. Something else for you to practice. 99 times anything is 100 times anything minus that original number, and that's all I've done here. Plus, and then there's no change to 75 over 99, 0. And now once again, we can bring this home. When we add 7698 to 75, we're going to get 7698 divided by 9900. And once again, using your divisibility rules or dividing by 2s and 3s and 4s or whatever you can, you should quickly find out that 6 is a common factor between the numerator and the denominator, which gives us a final answer of 1283 over 1650. Boom, just like that. So there's enough solved examples to help you get your heads around this idea of rational numbers and what they are and how they work. Okay, we've done definitions. We looked at the 3 forms of rational numbers can take. Well, 4 forms if you include the decimal and the fraction forms. Cool. And then we worked through a whole bunch of examples. Remember, you're not going to see very many examples like this in your questions, but the algebra you're doing and you've just done and helpfully reviewed with is going to be very helpful moving forward. So what do I have for you afterwards? I've got some practice questions and the solved solutions key linked as a PDF down below. Just go take a look. Give these a try. And if you want to check your work, you can compare yours to my solutions key and see what you're doing right and what you might need to work at or think about moving forward, okay? But the idea of being able to do rational numbers But the idea of being able to understand rational numbers that convert back and forth between decimal and fractional forms efficiently and correctly is going to be super important moving forward into high school. And I've left a little bit of room here for you should you wish to make some notes or some annotations. The goal here is to write the steps you use to get to the answers in your own words, so that when you come back to this in a month or 2, or maybe next year when we hit this again, that you can understand the process you took to get the job done, okay? So there we go, we're done. I'm going to leave you with the questions, and I will come back to you in the next lesson when we do a little bit of work at adding and subtracting rational numbers. Okay, you've already done adding and subtracting fractions. Now we're adding and subtracting positive and negative fractions, okay? So there you go. Happy mathing. Be a mathlete. Go get them. Cheers.